All right, let's talk about digital logic. If you're getting into hardware engineering, this is for you. We're going to peel back the layers and get into the real rules, the stuff that makes sure billions of tiny parts can actually talk to each other without messing up. It's the bedrock of reliability.
We love to think of the digital world as these perfect, clean ones and zeros. It's so tidy, right? But the truth is, underneath all that perfection is a messy, chaotic world of analog voltage. We're talking fluctuations, dips, spikes, just pure real-world electrical noise.
So that begs the question, right? How on earth do billions, literally billions of components on a modern chip, all chattering away, communicate without a single error? I mean, every one has to be seen as a one and every zero a zero millions of times a second. How does that even work?
The answer? It all comes down to what you can think of as a strict engineering contract. Now, this isn't some document you sign. It's a set of hard and fast rules baked into every single logic component. As long as every component follows the contract, the system is reliable. But the second one component goes rogue, you get total chaos.
So here's our game plan for breaking down this contract. First, the voltage contract, making sure everyone's speaking the same language. Then, the workload contract, which is all about how much a single gate can handle. After that, we'll look at the energy contract, or the cost of all this communication, and we'll wrap it all up with a super handy checklist for you.
Okay, let's dive into our first section. This is maybe the most fundamental part of all, the voltage contract. It's all about making sure every component is speaking the exact same electrical language.
Think of it like a conversation. The gate on the left, that's our speaker, and the one on the right is our listener. Now, for this conversation to work, what the speaker says, its output voltage, has to be something the listener can understand, its input requirements. And you see that gap in the middle? That's the indeterminate range, the danger zone. If your signal ends up there, it's just garbage. It's neither a 1 nor a 0.
And these are the actual numbers that matter, the kind of stuff you'll find buried in a data sheet. Take a look at TTL. The contract says its high output, VOH min, is guaranteed to be at least 2.4 volts. But the receiving gate only needs to see 2.0 volts, or VIH min, to know it's a high. That little 0.4 volt difference, that's not an accident. That is our safety net. And you can see how different the numbers are for TTL versus CMOS. They're two of the biggest logic families you'll deal with, and it's like they speak different dialects.
And that built-in safety buffer we just talked about, it has a name, noise margin. And trust me, you need it. Because the real world is electrically messy. Your power supply isn't perfectly stable, temperatures change, other signals can cause interference, all kinds of stuff. The noise margin is basically how much abuse your signal can take before the receiving gate gets confused and makes a mistake.
And we can actually put a number on that buffer. For a high signal, your noise margin is simply what the speaker promises to deliver. That's VOH min, minus what the listener needs to hear. That's VIH min. Same idea for a low signal. You take the maximum voltage the listener will accept as a low and subtract the maximum voltage the speaker will ever output for a low. The bigger that final number, the more resilient your circuit is going to be.
Okay, so we've got the language down. Every component knows what a high and a low is supposed to look like. But now we have to talk about workload. Just how much can one of these gates actually do?
First, let's get a quick term out of the way, fan-in. It's super simple. It's just the number of inputs a gate has. So this 8-input NAND gate you see here, it has a fan-in of 8. It's just how many different signals it can pay attention to at the same time.
Okay, but fan-in is the easy one. The one you really have to worry about as an engineer is fan-out. This is the big one. It's the maximum number of other gates that a single output can reliably drive without breaking its voltage promises. It's like how many listeners can one speaker talk to at the same time before its voice gets too quiet to hear. And it all boils down to how much electrical current that output can provide.
And let me tell you, violating this rule is a huge deal. If you try to one-gate drive too many others, if you exceed its fan-out, you are asking for trouble. Its output voltage will start to sag, right down into that forbidden zone we talked about, and boom, you've got errors. The chip itself will get hotter, it'll become less reliable, and eventually it could just fail completely. This is a textbook cause for those nightmare bugs that are impossible to track down.
So how do we know the limit? It's all about current. When an output is high, it has to source current. It's actively pushing electricity out. When it's low, it has to sink current. It's pulling electricity in. A gate can usually do one of these things better than the other. And your fan-out? It's limited by whichever one is the weaker of the two. It really is a case of a chain only being as strong as its weakest link.
Okay, let's actually run the numbers. It's pretty straightforward. First, to find the high state capability, we take the current it can source, IOH, and divide it by the current each input needs, IIH. So 0.8 milliamps divided by 16 microamps, that gives us 50. So it could drive 50 inputs when it's high. Now for the low state. We take the current it can sink, IOL, and divide by what each input needs, IIL. That's 16 milliamps over 0.4 milliamps, which is 40. See? We have two different numbers, 50 and 40. We have to be safe, so we always take the smaller one. That means the fan out for this gate is 40. It can safely drive 40 inputs. Not 41, 40.
All right, we've talked voltage levels and we've talked workload. Let's get to the final piece of the contract, energy. Because all this communication isn't free. It costs power.
And this is a really big deal when you're designing something. The two major logic families, TTL and CMOS, could not be more different here. TTL is, well, it's kind of old school. It's always drawing power, whether it's sitting at high or sitting at low. But CMOS, it's a whole different beast. It's incredibly efficient. When it's just holding a state, it's using almost zero power. It only really draws current during that tiny moment it switches from one state to the other.
So if you're calculating power for a TTL circuit, it's pretty simple. You just average the current it draws in both the high and low states, then multiply by your supply voltage. The actual power it uses to switch is so small in comparison that we basically just ignore it.
Now for CMOS, you flip that thinking on its head. The current it uses just sitting there, what we call static current, is practically zero. It's so small. So almost all of the power consumption comes from that transition current, when it switches from high to low or back again. And that right there is why pretty much every battery-powered device on the planet, from your phone to your watch, is built on CMOS. If the circuits aren't flipping states, they're not draining your battery.
Okay, we've gone through the whole contract. Voltage, workload, and energy. So let's boil all this down into a simple checklist you can use on every single design.
Number 1, respect the voltage contract. Read the data sheet and know your VOH, VOL, VIH, and VIL. Number 2, make sure you have enough noise margin. Think about the environment your circuit will live in. 3, never ever exceed a gate's fan-out. Do the math. 4, choose the right tool for the job. Pick your logic family based on your power and performance needs. And the most important thing to remember is that these aren't just suggestions. They are hard guarantees. They're the reason any of this stuff works at all.
So that leaves us with one last thing to think about. As we keep pushing the envelope, making circuits faster, components smaller, running them on lower and lower voltages, which part of this contract is going to be the hardest to uphold? Is it going to be maintaining a decent noise margin when voltages are already tiny? Or will it be managing the current load of fan-out when everything is packed so tightly together? That right there is the challenge for the next generation of hardware engineers.